Good afternoon, everyone. It's a great pleasure to be here. My name is Tommaso Macrì. I'm the Executive Account Manager at QueRa. QueRa is a quantum computing company whose mission is to build scalable, which means with a large number of qubits, error-corrected devices based on a specific technology which is called neutral atom quantum computing. QueRa is based in Boston, in Massachusetts, in the US. We employ a little bit more than 50 between scientists and engineers coming from our partner institutions, Harvard, MIT, and other top-tier universities all around the world. We productize innovations at very high speed, coming either from our R&D labs at QueRa or from the labs of our partnering institutions, Harvard and MIT. We already have machines that work. We work together, we partner with dozens of organizations and hundreds of users that already execute jobs on our quantum computer. Especially for those who are young and they are finalizing their studies, please feel free to check our openings. We are constantly hiring, so please check current job opportunities. QueRa, a little bit of history, was born back in 2019 as a spin-off of Harvard and MIT. And we closely follow the scientific breakthroughs that were exposed very clearly yesterday by one of our founders, Misha Lukin, that presented his lecture in the afternoon yesterday. Our first big milestone was the installation or the availability of our 256-qubit machine called Aquila on the platform of Amazon, the AWS bracket. And currently, this machine is actually the largest in terms of number of qubits that is available on a public cloud. Since then, we basically collaborated very closely with our academic partners to improve the capabilities of our quantum computing devices, demonstrating very high, basically world record 99.5 2-qubit fidelities, which is actually very important to then develop and deploy quantum error-corrected machines. And more recently, back in December, we were able to demonstrate the realization or the execution of complex algorithms with up to 48 logical qubits. And the concept of logical qubit is actually central to the whole idea of error-corrected machines, so machines that are actually resistant to the presence of environmental noise. Of course, that's not the end of the story. We have a rather ambitious, but not crazy, or paraphrasing what John Preskill, one of the founders of the modern theory of quantum information theory, said, quantum roadmap. We are actually planning to develop quantum computers that will have more than 10,000 qubits by the end of 2026, and these 10,000 physical qubits will then be able to encode about 100 logical qubits. Now, these 100 logical qubits seems like sort of arbitrary number, but that's actually quite important because we already know nowadays that if you want to simulate with classical techniques more than 50 qubits, it's already quite challenging with the current capabilities of classical supercomputing devices. The other thing is that we expect that with about 100 logical qubits, we will be able to already produce some useful quantum applications that will then be available for the pipeline of business of several enterprises across different business verticals. Before going into the details of how we plan to achieve these very relevant and ambitious results, let me make a step back and tell you very briefly how quantum computers or neutral atom quantum computers work. So first of all, why neutral atoms? Neutral atoms are in a sense natural qubits, because differently from other platforms which provide, for example, artificial qubits that you have to manufacture individually and characterize individually, neutral atoms are by nature all identical. They are pure and relatively resistant to noise. They are scalable. We already have, as Misha said yesterday, in our devices, naturally, several hundreds of thousands of qubits, if not millions. Then, of course, the challenge is to control those qubits. Nowadays, we provide or we make available to our customers and partners a machine with 256 qubits, but easily will be possible also to scale it up to a few thousands of qubits, as I said before. On top of that, controlling these qubits is actually very much easier with respect to other platforms or technologies because you require a much lower number of controls. So if you take an example, the case of superconducting qubits, typically you need 2 or 3 control lines per qubit. Here we are talking of about 10 control pulses for about 300 or 400 qubits. So a much lower overhead in terms of the number of controls. And last but not least, our quantum computers work at room temperature, again reducing the complexity and the footprint of our devices. From the physical standpoint, the possibility of encoding different types of qubit-based states into the electronic states of our atoms allow the possibility of basically producing or operating the computers with 2 different quantum computing paradigms. The so-called analog quantum computer that basically represent a continuous time evolution on top of the fact that you can also arrange the geometry of your array of qubits in essentially an arbitrary way. What you see there on the left of the slide is basically a map of the world that is made out of our rubidium atom qubits. The other modality that consists in the encoding of the qubit-based states into the hyperfine states of rubidium, so basically 2 states that belong to the manifold of the ground state of our atoms, allow much longer coherent times and therefore the possibility of realizing complex circuits in the standard way. So we have a set of native gates, like for example this Hadamard or some other types of control Z or control NOT that can be realized in different ways by applying techniques from AMO in the specific setup that we develop. And therefore then we can, on top of this, by using these tools, then develop complex algorithms that can solve practical problems. So summarizing, we have essentially 3 main ingredients or building blocks. The first one are the atoms that are represented by these little spheres. We can control the internal states and trap these atoms through very tightly focused laser fields, which are called optical tweezers. And we can then control the interactions and therefore the entanglement properties of these atoms by again manipulating the distance between these particles. So if we put the 2 atoms very far apart, basically they will not interact and we can excite them simultaneously to the excited state. In this case, this excited state is called the Rydberg state. If we put them together instead, the strong repulsion between these highly excited states will make basically the doubly excited state not available, not accessible, and therefore this opens up the possibility of creating complex entangling gates that are at the basis of the digital quantum computing that I was explaining before. This is also important for realizing complex many-body or entangled states in the analog regime that is the other modality or complementary modality to the digital one. So our quantum computer called Aquila completed a year in November of the last year. Over this past year, we increased the availability window from 10 hours to 100 hours. And we are constantly working with our partners across a wide spectrum of applications, simulation, optimization, and machine learning. So I will not have time, of course, to go into the very fine details of each one of these applications, but let me mention a couple. From machine learning, the possibility of implementing a new type of algorithm that exploits all the features of our analog device by basically providing different encodings of features of, for example, in a classification problem where we have to detect or decide whether an image is a horse or a penguin or a cat or a dog. And finally, providing a response by removing all the complexity of the intrinsic inner layers of or trainability of classical neural networks that are hard to reproduce in the quantum context. So in this case, for example, by applying this algorithm to a sort of standard data set which is called MNIST, that consists in the multi-class classification of handwritten digits from 0 to 9, what we saw is that by applying a sort of downsampling algorithm or which is in this case a simple PCA or principal component analysis, plus our quantum reservoir computing algorithm, we basically match, even with a small number of qubits, basically the performance of a classical neural networks applied on top of a standard PCA algorithm. Very recently, we advertised in a webinar that appeared last week, and I would be happy actually to share the link with you for those who are interested in learning more about the capabilities of this very exciting direction. Some simulation on our quantum machine with up to 108 qubits. So as of today, these are really the largest execution in terms of number of qubits of a complex algorithm like the one that we are displaying here. The other direction that, of course, we are pursuing very much with our now academic partners is the area of quantum simulation. Quantum simulation that, as was anticipated yesterday by Misha, is an area that was initiated almost 40 years ago by a very famous physicist, Nobel Prize winner, Richard Feynman, that basically, whose initial idea was to simulate a quantum system with a much more controllable and tunable quantum system. In this case, our 256 qubit machine. And what we see here is that there are plenty of examples, depending, of course, on the expertise of our scientists and our partners, across a wide spectrum of areas, from high-energy physics, quantum chemistry, and condensed matter. And of course, some of them are also easily translatable into some more business-wise areas, like, for example, quantum chemistry for dark design, as we've heard, for example, in the previous talk. Now, what are the challenges? What is the direction that we are trying to pursue at QuEra over the next few years? As you probably heard yesterday in Misha's talk, we are really moving towards the direction of digital or gate-based quantum computing. And here, again, the whole idea is to apply complex algorithms that are based on this mathematical and physical area of quantum error correction in order to boost the capabilities of algorithms that require a lot of resources in terms of number of qubits and in terms of number of steps or execution steps in order to get a meaningful answer. There are essentially 4 main building blocks in order to achieve these results. One of them is, of course, the use of neutral atoms as intrinsic qubits. Then the possibility of moving atoms around, which is called qubit shuttling. The possibility of performing parallel operations to realize native operations between logical qubits, so ensemble of qubits that reproduce in a much more coherent way the behavior of a single qubit. And finally, the possibility of using a zone architecture which resembles very much the behavior of classical computers, like, for example, our laptops. So in this picture, what you see is essentially a storage region or a memory region where basically we locate or we position all the qubits, either physical or logical, that are not actually at that specific instant of time under the execution of a specific operation. A second region, which is called an entangling region, where we basically shine laser and apply pulses in order to produce operations in parallel over many qubits. And finally, a readout region where we can basically take measurements either at the end of the algorithm or during the algorithm, realizing what are called mid-circuit measurements that are, again, another important building block to realize meaningful quantum error correcting codes. This culminated in this very relevant article that was published back in December of 2023, and of course, I would like to share with you the reference, what was mentioned also yesterday in Misha's presentation. But then from the partnership or from the application perspective, QueRa is certainly very ambitious in terms of realizing or contributing to the whole global quantum ecosystem. These collaborations, of course, go across both the academic side, the technological aspects by working closely with the companies, national labs, and HPC centers, but also more at a higher level, together directly with governments and with venture capitals in order to boost the creation, for example, the incubation of new companies that can be built on top of the technology that we are developing. So for example, we are closely working with BMW, with Deloitte, and with the global energy company across a wide spectrum of applications that embrace the areas of optimization and machine learning. But we are also working with innovation ecosystems such as Kai Ventures, that was also mentioned before in the previous presentation, to provide access to our quantum computers and education resources. And in parallel, we are also closely collaborating with several UK entities. For example, the Welcome Leap program, we have been very successful in the early demonstrations of applications, for example, of new designs for drugs for rare genetic diseases. And more broadly, with the QuEra that is also represented here in this event, in order to deploy one of our quantum computers in 2025. And finally, the announcement that was made a few weeks ago of the partnership with NVIDIA to deploy to AIST, essentially the equivalent of NIST in Japan, a quantum computer that will basically provide a quantum node to a much broader classical supercomputing, which is called ABCI. So, to conclude, let me stimulate, of course, discussions between all of you and us. I would be very happy to interact with you at different levels, both on the academic side, if you want to explore applications for fundamental research, or with companies, of course, to develop applications that are relevant to businesses, and of course, more broadly, with HPC centers and governments and the venture capital entities. So with this, thank you so much for the attention, and I'm open for questions. Thank you.
Thank you. We're going to have a short Q&A session. 자, 이제 질문 혹시 있으신 분 손 들어주시면 저희 스텝이 마이크 전달해 드리도록 하겠습니다. 혹시 발표 들으시면서 궁금한 점 생기셨던 분들 있으실까요?
Thank you for the insightful presentation. To my understanding, the Achilles heel of the neutral atom architecture is the long readout times. So I was wondering what approach QuEra is taking in order to reduce the readout time.
That's a good question. So there are different techniques that have been proposed. There are a couple of papers that I can suggest and we can discuss after the presentation. So of course there are two different ways that we can approach that problem, both at the hardware and the software level. I would be happy to discuss the technicalities after the presentation, of course.
Thank you for your very informative and great talk. And my question is, from your talk, there are two applications of QuEra. One is the quantum simulator using Rydberg state, and also there is some kind of other part that is quantum digital. There is some, one thing is quantum simulator and other thing is using 2-qubit gates. And when on the purpose of the quantum simulator, you make two atoms in entangled state using Rydberg bracket. But when you use the atoms to compute some quantum computing, you use two hyperfine states, not Rydberg states. So my question is how to make those two hyperfine states in entangled state without using Rydberg bracket.
Oh, that's a very good question. So there are, what you're referring to is the difference between analog and digital quantum computing. But let me tell you, so in both cases, we make use of the Rydberg states. The fact is that in the analog mode, the Rydberg state is already part of the encoding of the qubit basis states. So we have one hyperfine state and one Rydberg state. Okay. This, of course, will restrict or will reduce the coherence time. So the number of operations that we can perform, if you want, in the analog way, is much shorter or much smaller. Typically, the coherence time is of the order of few microseconds. Sorry. In the digital case, we make use of the basis states that are two hyperfine states. But then in order to create entanglement, or if you want a 2-qubit gate or 3-qubit gate, and so on and so forth, we need to excite one of the two states into an excited Rydberg state. So in both cases, we make use of the Rydbergs. but of course for different purposes and in different ways. In the digital case, the fact that we encode the basis states of the qubit into two hyperfine states will instead allow for much longer coherence times of the order of 1 or 2 seconds. Okay, so this will, in principle, allow several thousands of operations or even more, depending on the speed, of course, of the operation itself. But we can, of course, I'm happy to respond more in detail if you want after the presentation.
퀀텀 컴퓨팅이 여러 분야에 사용이 되겠지만
Wait a second.
네, 다시 지금 리시버를 착용하시고 다시 한 번만 네, 질문 시작해 주십시오. 고맙습니다.
네, 퀀텀 컴퓨팅 분야가 여러 응용에 쓰일 텐데요. 바이오 분야에 대해서 현재 스테이터스하고 그리고 좀 발전 방향이랄까요? 시간 정도 좀 예측이 가능할까요?
Yeah, that's a very good question. So the question for those who do not have the live translation was about the applications in bio and what is the characteristics timeline associated to those applications. Well, there are two different problems here. One is, of course, the hardware development, and what I basically showed at the very beginning is that we have a roadmap to basically increase the capabilities of our quantum computers to several tens of thousands of qubits. Now the question is, are these qubits enough in order to sort of provide some useful applications? The answer is that this is still a part of the algorithm development, which is the second part of the answer that I wanted to give. So the answer is, it depends. So we are actually working on two different fronts. The hardware development, which is essentially at the core of the things that we want to do at QueRa, but at the same time we want to develop what is called the killer app, the killer applications, which might well be in the field of bio. What I was sort of anticipating is that QueRa is actively working together with several partners, including international organizations like this Welcome Leap that I was mentioning through the presentation, for example, in the field of designing new types of drugs. But of course, the field is very broad, and there are different types of approaches that can be used, both by employing what I define the analog quantum computing capabilities, or more likely the digital capabilities. Or there might be even hybrid approaches where we use both. And hybrid here can mean both analog plus digital, or even the use of a quantum node associated to a very large classical HPC center. So in principle, the question is very open-ended. There is no definitive response. In terms of timeline, I would say that there is a clear timeline for the development of the hardware. It is less clear in my personal opinion, what is the development of useful applications that will make use of that specific capabilities of quantum computing devices.
네, 고맙습니다.